All right, Chem 11 people, we're back. My next lecture is on combustion reactions, obviously, and why my class is straight fire, and you know it. Again, we've got the same setup as usual. My iPad is up here in the corner. That has the lecture notes that I posted for you online, and then we'll use this to help along with that material, and I'll write some diagrams and some equations in that here on the whiteboard. So let's get started with our discussion of combustion reactions. This is online for you. This note through your D2L page. So a combustion reaction is a reaction between two substances. A fuel of some sort. Now the fuel can be a variety of different things, and we'll go over a bunch of different fuels as this lecture progresses. But the other thing is only one thing, and it's oxygen. So you have some sort of fuel and oxygen. And it reacts very, very rapidly to produce carbon dioxide and water. So we always have some sort of fuel. Now notice I'm not writing a formula for fuel because that can be a whole bunch of different things. Oxygen we know is a diatomic gas, and then CO2 and H2O are produced. So we always get these two products, and this is always one of our reactants. The only thing that can change is this, but these are there in all combustion reactions. These reactions occur very rapidly. They produce a lot of energy, right? Even inefficient burning still produces a lot of energy. A fire can be, just barely burning, and if you put your hand too close to it, you'll get burned. There's a lot of energy there. And of course, if the fire is raging, you don't have to be even that close to the fire to feel it. So a tremendous amount of energy can be given off in a very short period of time. Our general equation, well, we've already got that written down here, is a fuel and oxygen giving us CO2 and H2O. And these three things right here, this is what we're always looking for. Something plus oxygen giving us these two products. And the fuel quite often has this type of a formula. It's a hydrocarbon. A hydrocarbon has just two elements, hydrogen and carbon. And we can see here that these numbers, I've left them blank. And that's because different hydrocarbons have different formulas, right? I'll do two of them really quickly. Propane in your barbecue is C3H8. Ethine, which is used in your shop class for welding if you take auto, is C2H2. And octane, which is in your gasoline, octa for 8 carbons, is C8H18. But we can see the carbon and hydrogen are the same throughout. It's just the ratio, the numbers that are changing. All right? So one of these types of things end up usually here. So the hint, well, something, usually with this combination of elements, reacts with oxygen to give us these two products every time. All right? Now, if I go over some common combustion reactions, I'll move this because we're not ready to do incomplete combustion just yet. Move that out of the way, and we'll go over several examples of balanced equations. Now, there's two types of combustion. There's complete combustion. If it is a complete combustion, it means that oxygen level is high. O2 is high, right? So I'll put squared brackets around that. That indicates concentration. A complete combustion, oxygen levels are high, the fuel totally combusts, and you only get the two products, carbon dioxide and water. So let's go over a few of those. A complete combustion usually gives us a blue flame. When we did the flame test lab, we were burning the natural gas that was coming through our ducts in the classroom, and we could see that, sorry, I should say out of the gas jets in the classroom, and we could see that a blue flame was produced when we opened up the base of the Bunsen burners, allowed more oxygen in there, all right? An orange or red flame usually means an incomplete combustion, which we'll cover momentarily. So our first example is going to be a very simple hydrocarbon called methane. Methane is as easy as it gets for hydrocarbon. It's just CH4, only one carbon in there. And it combines with oxygen. And of course, we're going to get CO2 and H2O. So now we're going to fill in a little bit of information. Now we have to start putting in states into things. So this is a gas. Oxygen, we already know that's a gas. Carbon dioxide is a gas. And water is a liquid normally. But because we have a tremendous amount of energy being released by these combustion reactions, the water is no longer a liquid. It's a gas. It's so hot that the water vaporizes. It evaporates, right? So that's why when you burn a log in your fireplace, you don't see a pool of water collecting below the log as it burns. It's so hot that the water vaporizes. It basically boils really, really quickly and goes up into the atmosphere. So, and of course we're going to balance this equation. So to balance this equation, we simply need a 2 here, and we need a 2 here, and that will balance that equation off. All right? Another common example. We just talked about this one. This is propane. And again, the rest of it is the same. The complete combustion of propane. Again, you see the pattern. The oxygen is the same. The carbon dioxide is the same. The water is the same, right? The only thing that changes is this fuel. This is a gas. This is a gas. This is a gas. And that is a gas, right? We're used to it being a liquid, but it's a gas because of the high temperature. And of course, to balance this one off, I need a 5 here, a 3 here, and a 4 here. So that's the combustion of propane, like in a barbecue tank up at your trailer or cottage, or even in your backyard, all right? When you turn your barbecue tank on, you usually see that the flame is a blue flame. If your barbecue is in good shape, it'll be a blue flame, which indicates that it's a complete combustion, right? It's very efficient, very hot flame. So those are some common ones. I'll do one more for you, just so we can see the pattern one last time. And this last one is going to feature another hydrocarbon, C4H10. Now C4H10 is butane. We'll put our states in. Again, all gases. And so to balance this one off, the numbers get a little bit more intricate. They're tricky, right? And so here we got to double this. In an earlier lecture, I talked about balancing equations, and I said sometimes you get something that's going to have always an even number of oxygens here, but something over here may make it odd, so you double everything. This one was like that. You had to double everything to get to the proper balancing. So there's a 2, a 13, an 8, and a 10 involved here, right? So that's butane, like in a lighter that you'd buy at the Dollarama, the best store on earth. And when you light it, I know it looks like a liquid in there, but when it comes out of the top and mixes with the oxygen, it is a gas, right? When you push the little button down on the lighter, you hear it's, you know, if you put your ear up close to it, but it's not spraying out a liquid. The butane vaporizes and it's a gas. All right? So, but you can see the same pattern there, a fuel and oxygen giving us carbon dioxide and water. Now, we'll bring this back in. Now, sometimes we have an incomplete combustion, and an incomplete combustion has a lower level of oxygen. So, incomplete combustion oxygen concentration is lower. Now, oxygen is one of our two reactants needed to burn something, right? If I take oxygen away from whatever's burning, it won't burn anymore, right? A fire blanket is supposed to be used on people. What that does is acts as a barrier between the oxygen in the room and the person, so the person stops burning, right? When you throw water on something that is burning, the water displaces the oxygen around the object and it stops burning. So when we have lower levels of oxygen, we have lower levels of burning, lower levels of combustion. And what happens is, well, the burning is a lot less efficient. It's not nearly as hot as it could be, and our energy output kind of correlates to that. It's a lot less efficient as well, a lot lower in energy output. So, the products of an incomplete combustion are kind of tricky because as you go from a complete combustion where there's a ton of oxygen and you slowly bring that oxygen down, the amounts of each of these products starts to change. So I'll mention all four of them. There's two more additional products that we're going to have to bring into play here. And we can see them here. We end up with, again, we've got our fuel, we've got our oxygen. Now, these two can be there. Sometimes if it's very, very low, carbon dioxide will not be there, but it will be if we still have a fair amount of oxygen. So we have carbon dioxide. We saw that before at the complete combustion. We have water. We saw that before. But now we've got these two. Carbon monoxide is a gas, right? These will all be gases. If I put the states in here very quickly. Carbon monoxide is a clear, transparent, fancier word, a transparent, odorless gas. You can't smell it, you can't see it, so you don't even know it's around you. But what it does is it jumps into your blood when you breathe it in and displaces the oxygen. It adheres to your hemoglobin, and basically, if there's no oxygen in your body, you need oxygen to make energy, and if there is none, your energy levels drop and you die, right? The carbon here is a solid. So it actually is the soot or the ash that you see, right? So that if you go, if you have a fireplace, you actually burn logs. It's not a natural gas fireplace. As you burn the logs, ever so often you got to get your chimney swept because the carbon residue, the solid carbon, sticks to the walls of the chimney. And if it gets too thick, it can be a fire hazard. Designers of car engines, they obviously want complete combustion as much as they can have. Because if you get this building up, this is going to stick to the inner walls of your piston chambers, and then the car doesn't work as well. Your energy output, right, isn't as good. The pistons start to stick as they're going through the chambers, and you want the pistons to go as fast as they can, because the faster the pistons go, the faster they drive the car. So you don't want an incomplete combustion reaction in your car engine because of the solid that gathers here. These will just go out through your tailpipe. Anyway, let's look at a couple of examples here. So that's the end of our lecture. There's Professor Frank there. This is certainly not junk, but... So let's go through a few examples. And again, those four products that we just had, the amounts of them are different for different levels of oxygen. So the first one, what if we took our propane? So that was C3H8, and again we added oxygen. This is a gas, this is a gas, And this time, we didn't really put a whole lot of oxygen in there. The oxygen level was lower. Propane didn't burn quite as efficiently. What we end up with is, well, CO2 and H2O. We also end up with carbon monoxide and carbon. And again, this is a gas, that's a gas, that's a gas, and this is solid. This may build up. If this is a barbecue and we're burning propane, this may end up inside of, on the inner walls of your barbecue, right? Or on the burner. To balance this one out, it's a bit tricky. And what we do is we put a 2 here, a 7 here, a 2 here. You can tell this would be quite a job. An 8 there, and a 2 there, and a 2 there. But again, if I lower this even more, the ratios of these will change. If I up this even more, the ratios of these will even change. So for all intents and purposes in our class, I might ask you what the 4 products are of an incomplete combustion, but I'm not going to get you to balance these equations. If you're going to have to construct one and balance it, it very likely will be a complete combustion, where we just have the 2 products, carbon dioxide and water. And again, we use the car as the example, so let's do that again. Here's gasoline. I know you buy it as a liquid, but when it gets into the piston chamber where it combusts, it is a gas. It's mixed with oxygen, which is also a gas. And we get these products, and of course gas. Gas, normally these little G's would go in behind these things, but the whiteboard is not huge. And to balance this one off, we simply add a 9 here, a 2 here, and a 9 here, and a 5 right there. So that one's balanced, and again, as the levels of oxygen go up or down, it can change the ratio of these. So we should still be able to come up with a skeleton equation, name the 4 products, but the balancing will kind of leave that off. All right? Anyway, that's our 2 types of combustion: complete combustion, high efficiency, high oxygen, high temperature, really hot fire, and incomplete combustion. Lower oxygen, less efficient, not quite as hot. Both take place in everyday life, and that's it. That's all about burning stuff. Anyway, hope you enjoyed the lecture. I'll talk to you soon. If you have any questions, reach out to me through Edsby or make a comment on the YouTube video. All right, thanks. Talk to you later. Bye.